of last year. So my name is Hannah Besso. I'm presenting on work that I did as part of my master's thesis that I defended in November of 2022. I'm going to get rid of this. And the title of that research is Mountain Snow Depth Retrievals from ICESat-2 SlideRule Satellite Laser Altimetry. I want to acknowledge my co-authors and the committee members for my master's thesis, Jessica Lundquist and David Shean, who are professors at CEE here at UW.
One second. The screen that you're showing on here is what you're seeing on your computer screen instead of what's
Thank you.
being shown there. Sorry, I'm gonna stop it.
How's that?
Once it decides it wants to actually show me it's sharing. I think the internet is struggling a little bit.
It says the screen sharing is paused.
Oh, okay. Yeah, it says it's paused. Resume share.
This one? It's hard to see. Oh, here we go.
Yeah. Hopefully that will. There we go. That's great.
Okay. Everything look good?
Yep, it's great.
All right, so the title of my talk is Mountain Snow Depth Retrievals from ICESat-2 SlideRule Satellite Laser Altimetry. And just from that title, you might have a few questions about my research. So I'm going to create a roadmap that will help us stay organized throughout this talk. The first question we will address is, why is snow important? Then we will cover what are ICESat-2 and SlideRule. We will investigate how they can measure snow depth, to what accuracy they can measure snow depth, and then finally, what are the implications of this work? So let's jump in and answer the question, why is snow important? This here is kind of a generalized graph of the evolution of snow depth throughout a season. On the y-axis, we have snow depth, and on the x-axis, we have time. In the springtime, snow melts and creates stream flow. So during the winter and fall, we get the accumulation of snow, and this is the time when we like to go skiing in the mountains and play in the snow. In the springtime, it melts and fills our reservoirs, which then provides stream flow later in the summer for irrigation and our use as drinking water, etc. Climate change is making snow depth more variable and is potentially decreasing the amount of stream flow we might get from snowmelt. So we predict that in the future, there will be less snow and that it will melt out earlier in the season, which leads to less stream flow and earlier stream flow, which means we will have less reservoir storage and less late summer irrigation. Snow is also challenging to measure, and part of this is due to the variability of snow in both time and space. So this is one example of snow variability. We see that in the left image, which is taken at Crystal Mountain, we see that within one basin, we can have variable snow depth. On the right side of the image, there's no snow, whereas on the left side of the image, there is snow. And in time, within the span of just 1 month, we can have drastic changes in how deep snow depth is throughout a basin. So we're going to dive into this idea of time and space a little bit more. Here again is an image of snow depth evolution throughout a season. So here we're looking at the time domain. On the x-axis, we see we have time. And we can also look at this in the spatial domain. Here we have our x and y axes as latitude and longitude. So we're dealing in the spatial domain. Let's explore some of the snow measurements that currently exist. We have manual measurements that are taken by individual people going out into the field in a snowy environment and taking, for example, snow depth probes to probe how deep the snow is. This can give us information at single point locations in space and as many times in a season as people go out to collect these measurements. However, it can be difficult to access field stations in the wintertime due to road closures and the difficulty of plowing high mountain roads in the wintertime, and also due to the difficulty of accessing steep terrain that can be avalanche prone if someone is going on foot or skis. We also have weather stations that use telemetry to transmit information about the weather and the snowpack in real time. And these measurements are also single point locations, but they collect data throughout an entire season, so continuously in time. This is one example of what a station might look like that is measuring snow depth throughout a season. Airborne LiDAR can also collect information about snow. It does that via an airplane, which has a LiDAR instrument on board. The LiDAR instrument is able to send a light signal from the plane to the surface of the Earth. That light reflects off the surface of the Earth, returning to the airplane, and the amount of time it takes for the light to travel can be converted into surface elevation of the Earth, because we know the speed that light travels. This can be considered the gold standard of snow depth measurement in that it gets very high resolution data. And we can calculate snow depth using these measurements by doing a LiDAR flight during the snow off period and another during the snow on period. The difference between the elevations can give us snow depth. However, these measurements are extremely expensive and can only be conducted in select basins that have the resources to pay for this. Another measurement that we can use are measurements from satellites that orbit the Earth. And in general, these satellites have not historically been able to measure snow depth. And so that's why we see that we don't have any depth information here, but they can measure information distributed out spatially. So for example, here's an image, an example that we could get from satellite imagery showing extent of snow, but not depth of snow. And the depth is extremely important for us to be able to estimate volume of water that will melt out from that snow later in the season. And Lettenmeyer et al. 2015 said that among all areas of hydrologic remote sensing, snow and snow water equivalent in particular is the one that is most in need of new strategic thinking from the hydrologic community. And so that is some of the motivation for the work that we are going to do during this presentation. Finally, we can model snow depth, which can give us information in both time and space. However, depending on the inputs that we choose to give our models, we can get drastically different results that are not always constrained well. So this is just one example of different weather inputs, different meteorological forcings that are given to a snow model, and the differences that result between the results from both of those inputs can be on the order of 4 meters, which is quite a lot. So to recap, we asked the question, why is snow important? We discussed how snow provides stream flow to downstream users, that climate change is making snow more variable and important to measure, and that current measurement techniques don't in themselves provide enough information. We'll now tackle the question, what is ICESat-2 and what are SlideRule? So back to our measurements slide, I want to add ICESat-2 to our satellite options. So ICESat-2 was launched in 2018, so it's fairly new. And it is able to collect data at multiple points within a watershed. So that covers the spatial domain and at multiple points throughout a season in the temporal domain. ICESat-2 is a spaceborne LiDAR instrument. So we talked about airborne LiDAR, which uses airplanes. This is a LiDAR instrument mounted on board a satellite. It is polar orbiting with the primary goal of detecting change in elevation and mass on ice sheets at the poles. It repeats measurements at high latitudes at the polar regions every 3 months. It has very high accuracy 6-beam LiDAR that can measure centimeter scale vertical accuracy over polar ice sheets. And I want to highlight here, this is looking at the pole of the Earth. We get much greater spatial coverage at the poles because of that polar orbiting of ICESat-2. And as we get closer toward the equator, because of the curvature of the Earth, those measurements get spaced out in space. So we get lower spatial density of measurements and not repeat measurements. To dive into how ICESat-2 works in more detail, this is an illustration of the satellite with the 6-beam LiDAR that are arranged into 3 beam pairs. Now we'll zoom in on one beam pair to learn about how ICESat-2 works. As the satellite orbits the Earth, it sends out pulses of photons. And these photons are centered around a ground track that the satellite is orbiting over. Approximately every 70 centimeters on the ground, the satellite sends out a new photon pulse. And as it continues to orbit, these pulses of photons end up giving us information distributed about this ground track. We can zoom back out to all 6 beams and all 3 beam pairs. And if we imagine looking at the surface of the Earth from the perspective of the satellite, this is an illustration of what we would see. 6 tracks with multiple photon returns along each track. Now let's change our perspective from looking down at the surface of the Earth to looking sideways at an elevational profile of the Earth. So here we have a terrain side profile. We can imagine ICESat-2 orbiting over that terrain and collecting elevation information from these photon returns. And they'll be distributed about the true terrain surface elevation. There are several standard data products that we can access through NASA, NASA's the organization that was able to launch ICESat-2. And the NASA science team has developed several algorithms that process the raw photon returns into a product that scientists can access and ask research questions about. So one of those products is the land ice height product. And this is one of the ICESat-2 products that has in the past been used to try to measure snow depth. To produce the land ice height product, the NASA algorithm fits a best fit line to the photon returns. And that best fit line in this case is 40 meters long, with mean elevations aggregated along at the center of each of those best fit lines. And these points end up being 20 meters apart along that ICESat-2 track because the segments are overlapping. So we get a point every 20 meters. However, it does not differentiate between different types of terrain. So we might have the ground surface and we might have canopy cover over that ground surface. And this product does not differentiate between canopy cover and ground cover. And so if there are trees, that might positively bias the elevation that we're measuring. So past work has measured in treed and steep terrain that there can be 70 centimeter residuals or errors for this product when it tries to measure snow, when you try to measure snow depth using it. And those are pretty large residuals when we think about the depth of the snowpack. So we conclude that this might not be the ideal product to measure snow depth in treed and mountainous terrain, which is the majority of the regions in the Western US that have snowpack. You think about the Cascade Range, most of our snow is in the steep mountainous terrain that has lots of trees. Another standard product that has been used to try to measure snow depth is the land and vegetation height product. This has longer best fit lines, about 100 meters long, again, with mean elevations that centered along those tracks or along those segments. And this product is able to differentiate between canopy cover and ground cover. So if we are only interested in the ground, we can exclude information about the canopy cover. However, over very rough terrain, 100 meters is a long distance to aggregate elevation over. And so if there are elevation differences that are at scales lower or smaller than a meter, or than 100 meters, those segments will not capture that variability. And previous work has showed that there can be residuals greater than 1 meter in steep terrain using this product. So once again, that's a lot of error when we think about the typical depth of the snowpack, which at the most might be up to 3 meters in many places. So we conclude that this also is not an ideal product to measure snow depth in mountainous terrain. So neither of these products we've determined is ideal in these terrain. And this was me in February of 2022, having tried to measure snow depth using both of these products and finding that the residuals were just too great to measure accurate snow depth. But luckily, there was a group of intrepid researchers at both NASA and the University of Washington who had noticed the same issues with this data and decided to make a customizing tool that allows scientists to customize the parameters used to process ICESat-2 data so that we can use it for questions that were not part of the primary aims of the satellite. But no research has been published yet that proves that the SlideRule product is better than the standard products that are produced from the NASA algorithms. And so we don't know how well we'll perform in the areas of the Western US where all of our snow depth tends to occur. So using ICESat-2 SlideRule, we are able to customize the parameters, as I mentioned, that go into processing ICESat-2 data. So we can choose to use those short best fit lines like we saw in the land ice product. So we choose 40-meter long segment lines. And we can also choose to only use photons that were reflected from the ground surface instead of the canopy cover. So this is kind of like taking the best of both worlds from the products that we saw earlier and combining them. But we still don't know how well they will perform. Oops. To recap a little bit, ICESat-2 was intended to be used at the poles, where you can measure direct change detection using the repeat elevation measurements from ICESat-2, and where terrain is mostly smooth, think about an ice cap, with no vegetation. And we want to be able to use it for something it was not intended to be used for originally, to measure snow depth in the Western US, in areas where we do not get repeat ICESat-2 elevation measurements, where we have rough terrain and treed areas. So our goals are to address these challenges with using ICESat-2 in the Western US, the lack of coverage, lack of repeat coverage, the rough terrain, and forest cover. We ask, how can SlideRule improve ICESat-2 snow depth accuracy, and in what terrain can we confidently apply these techniques? We'll do a quick recap again and move on to our next question. So ICESat-2 is a satellite LiDAR instrument that measures surface elevation. Sorry, it's not the instrument, it's the satellite that the LiDAR instrument is on board. Standard products have too much uncertainty at mid-latitudes to measure accurate snow depth. And SlideRule is a new processing tool that allows us to customize ICESat-2 data. We'll move on to ask how ICESat-2 SlideRule can measure snow depth. So because of the lack of repeat coverage from ICESat-2, we need to pull in an outside data source. And this will be a snow off elevation data set, again from airborne LiDAR, that will give us the baseline for our measurements. We will also use our ICESat-2 SlideRule elevations that were collected during the snow on time of the season. For our accuracy assessment, we will use ground truth snow measurements like we discussed earlier, the aerial LiDAR surveys from the snow on time period, snow weather station telemetry, and manual snow depth measurements. Our first step will be to sample the snow off elevations from the snow off elevation map at each of the points where we have an ICESat-2 elevation measurement. We can then take the difference between these elevations, the snow off measurement and the snow on measurement from ICESat-2, to calculate snow depth. We then aggregate all of those snow depth measurements to get the median snow depth from a specific ICESat-2 acquisition date. And finally, we can compare that snow depth to the ground truth measurements that we talked about earlier. Now we need somewhere to study this, so we are going to dive into some details about our two study sites, the Upper Tuolumne River watershed in California, which is located within Yosemite National Park in the Sierra Nevada, and the Methow Valley, which is on the eastern side of the Cascade Range in Washington. The Upper Tuolumne River watershed is the source of water for San Francisco, and the Methow River contributes to local farmland and to the Columbia River. For data availability, both Tuolumne and the Methow Valley have the snow off aerial LiDAR that will provide the baseline measurements for our calculations. The Tuolumne River shed has multiple telemetry weather stations within the basin, whereas the Methow Valley has these telemetry stations not located exactly within the bounds of the basin we'll be studying. Within Tuolumne, there are multiple aerial LiDAR surveys from the snow on period that provide very high resolution detail about snow depth distributed throughout the watershed, whereas in the Methow Valley, these do not exist. We do have a few sparse manual observations from the community snow observation project, where individual people have gone out and probed the snow. To compare some of the characteristics of these two sites, the Upper Tuolumne River watershed has about 30% tree cover. The Methow Valley has about 45% tree cover. The Methow Valley is about 3 times as rough as the Tuolumne River watershed. The specific numbers here you don't need to pay too much attention to, but the important thing to take away from this is that the Methow Valley is much rougher terrain than Tuolumne. And finally, the median snow depth throughout the study period, that the 4 years of our study period, was about between 1 and 3 meters in Tuolumne and between about 1/2 and 3/4 of a meter in the Methow. So just from looking at these characteristics, we can make predictions about how well these study sites will perform when we try to compare ICESat-2 snow depth to ground observations. The lower percentage of tree cover, the smoother terrain, and the deeper snowpack that will provide more of a signal for measurement means that the Upper Tuolumne River watershed is likely to perform much better than the Methow. And so we're going to use these two sites to compare our results and try to investigate how the terrain and canopy cover in each of these produces different results when we look at ICESat-2 snow depth. So to recap our methods, the snow off aerial LiDAR elevations are different from the snow on ICESat-2 SlideRule elevations. And the median snow depth within the basin for each of the ICESat-2 acquisition dates can be calculated. And ICESat-2 SlideRule median snow depth is then compared to ground truth. And now we can dive into our results. What is the accuracy of the snow depth that we can calculate? So to dive into our results, I want to show these maps. On the left in gray, we have the elevation map for the Tuolumne site and some satellite imagery for the Methow site. Sorry, and satellite imagery for Tuolumne. And then on the right of the image here, we see the same products for the Methow Valley. And now we'll pull in some snow depth maps for both locations. So this is the snow depth as measured by ICESat-2 and the snow off elevations from aerial LiDAR. And at just first glance, we can see some spatial trends as to where we see the deepest snow depth at both of these locations. At the Tuolumne site, most of the deeper snow depths occur to the eastern side of the watershed. Where we also see from the snow off elevations is the highest elevation portion of the watershed and an area with less tree cover and smoother terrain. It tends to, in the upper Tuolumne River watershed, it's these beautiful granite slabs without a ton of vegetation, and they tend to be gently sloping granite slabs. Whereas in the Methow, most of our deep snow depth occurs on the western portion of the basin, where we also see from the elevation map that it is higher elevation with steeper slopes and with more vegetation. So this is some of the differences between the Sierra Nevada and the Cascade Range, is that in the Cascade Range, our high elevation, deep snow depth regions tend to have a lot of tree cover and tend to be very steep terrain that is also very difficult to traverse on. They're all like steep hiking. If anyone's hiked in the Cascades, you know, it's very steep and pretty dense canopy cover. Moving on to more results, we're looking here at a single year of snow depth, and this is the evolution of snow depth throughout the season at the two weather stations in the Tuolumne, at the Tuolumne site. And then we can bring in our ICESat-2 data. And I'll describe this in detail. It might be confusing at first. So the each date where ICESat-2 orbited over the watershed, we have a box plot here. The black line is the median snow depth as measured by ICESat-2, and the blue box is the interquartile range of snow depth. You can see that there's variability in the data, but that the median snow depth from one ICESat-2 acquisition date tends to trend with the snow depth as measured on the ground by the weather station plots. All right, this is about to get a little busier, so I'll explain in detail and try to go slow. As I mentioned, there is snow on aerial LiDAR data from the Tuolumne site. And this LiDAR was flown at multiple times throughout each season of our study period. On dates when the aerial LiDAR was flown within about 20 days of an ICESat-2 data acquisition, we can compare the snow depth between the two instruments in great detail. So in the red boxes, these are pairs of data, the blue being the ICESat-2 and the green being the aerial LiDAR data. The data was acquired within 20 days of each other. And we can see that the median values for both of these instruments are fairly close together. The aerial LiDAR data that I'm showing here is the data that was sampled at each specific location that ICESat-2 reports an elevation measurement. So remember, it's every 20 meters we get an elevation point. But we can also compare our aggregated ICESat-2 snow depth data to the snow depth in the entire basin. So here in purple, we're looking at data that was aggregated from the aerial LiDAR survey for the entire Tuolumne Basin. And we can see that the medians between the ICESat-2 in the black lines and the purple lines, which is the median for the basin snow depth, are remarkably close together, which is telling us that we are measuring very accurately the basin median snow depth using these ICESat-2 single acquisition dates. We've only been looking at a single year so far, the 2019 water year, but we also have this data for 4 different years through 2022. I won't show all the aerial LiDAR data because it gets messy, or it's just a lot to look at once, but we have this data for all 4 years and used it to compare our residuals to previous studies. Here we're looking more in depth at the paired data. So remember, we have ICESat-2 acquisition dates and aerial LiDAR acquisition dates within 20 days of each other. And those are sets of paired data. On the right, we see that sampled aerial LiDAR data compared to, on the x-axis, compared to the ICESat-2 data. And each of these points represents a single acquisition date pair. The median residual between these two data sets was 19 centimeters, which corresponds to a percent difference of 20%, and that's relative to the depth of the snowpack. On the left, we are looking at the same pairs, but this time we're comparing to the entire basin median snow depth instead of those individual points. Here we have a median residual of only 11 centimeters. The percent difference is 15% of the entire snowpack. And I want to compare that now to previous studies, which use those standard data products that saw in similar terrain, which is both steep and treed, residuals of 70 centimeters and greater than 1 meter. And I also want to point out that ICESat-2 has global coverage. And the fact that we are able to match this closely with the aerial LiDAR surveys has great potential for measuring snow depth globally, especially since that aerial LiDAR data is so expensive and difficult to collect in larger watersheds. We'll now move on to the Methow Valley site. You can kind of orient yourself to the study location based on the small icon on the left of the screen with the outline of Washington in it. So here we see the evolution of snow depth again using those telemetry weather stations. We can look at our manual measurements, which were located within our watershed. And this is mostly as a gut check to make sure that the measurements of snow depth within our watershed generally match the telemetry weather stations that are located slightly outside of our watershed to make sure that we're comparing similar snow depths. So now we can bring in our ICESat-2 snow depth data. Again, the black lines show the median depth and the blue boxes show the interquartile range of those measurements. And again, we see a decent amount of spread in our measurements, but that the median generally tracks showing that we do have a difference in signal between the snow on and snow off season. And we can look at this for all 4 years of data. And in general, just comparing these data to what we saw in Tuolumne, we see that the median snow depth in the Methow does tend to track slightly lower in general than the measured snow depth at our weather stations. We can compare our residuals at the first telemetry station that is measuring snow depth throughout the season. We see a residual difference with ICESat-2 snow depth of about 27 centimeters, which in the Methow, due to how much shallower the snowpack was, resulted in about a 52% difference. At the second weather station, we saw residuals of about 31 centimeters or 60% of the snowpack. And although this looks like high percentages when we look at the residuals compared to the depth of the snowpack, the absolute value of these residuals is still lower than that of previous research using standard products. To compare these two sites a bit more, we saw in the upper Tuolumne River watershed residuals of 19 centimeters for the aerial LiDAR survey that was sampled at each ICESat-2 location, 11 centimeters when compared to the snow depth in the entire basin, and about 21 to 46 centimeter residuals when compared to the weather stations. And I want to point out that our biggest residuals occur when we compare to those single point locations where we're collecting weather and snow data throughout the season. And in the Methow Valley, those are the only places we were able to compare to our ICESat-2 snow depth. So that tells us that these point locations are useful, but they might not be the most representative of snow depth in the entire basin. I also want to remind everyone that the deeper snow depths at our two different sites occurred in very different terrain. In Tuolumne, the deep snow depths occurred in regions with much smoother terrain and less canopy cover. And in the Methow, the deeper snow depth that we want to be measuring occurs in rougher areas with more vegetated terrain. To recap these results, the ICESat-2 SlideRule predicted basin snow depth within a median residual of 11 centimeters in Tuolumne. In all cases, across all comparisons, the accuracy was under 50 centimeters, and often much lower than that. And finally, the type of ground truth that we compare to matters, whether we're comparing to single point locations or spatially distributed data. Finally, let's move on to the implications of this work. Our research goal was to address the major challenges with using ICESat-2 to measure snow depth in the Western US. And those challenges included a lack of repeat data, difficulty measuring snow depth in rough terrain, and also in forest cover. To remind everyone, we were trying to evaluate the customized SlideRule product in steep and forested terrain because that is where most of the snow depth occurs in the Western United States. So to address the lack of repeat ICESat-2 data, we were able to bring in outside data sources to provide snow off elevation data from aerial LiDAR. We were able to address the rough terrain and forest cover using SlideRule, customized processing parameters to get median residuals of less than 50 centimeters. So to remind everyone, our question was, how can SlideRule improve ICESat-2 snow depth accuracy, and in what terrain can we confidently apply these techniques? We were able to measure snow depth with more accuracy. Our shorter best fit lines led to more accurate measurements in rough terrain, and our ground classifications led to more accurate measurements in treed terrain. In conclusion, ICESat-2 SlideRule was able to improve our results in forested and rough terrain. We were able to accurately predict base and median snow depth in Tuolumne within about 11 centimeters was our median residual. And at both sites, our median residuals were under 46 centimeters when compared to telemetry stations. In areas like the Methow Valley, where snow depth measurements are sparse and have been historically difficult for satellites to measure due to various factors such as large amounts of cloud cover in the wintertime when we have snow depth, and also very dense tree cover. In areas like this added data is especially important because it's adding to an already very sparse data set. And we also need more ground truth data in locations that pose difficulties for remotely sensed data, because we need high accuracy measurements so that we can compare these new remote sensing techniques to. ICESat-2 SlideRule provided high accuracy basin snow depth data in this terrain. However, one remaining challenge with this methodology is the need for high resolution snow off area LiDAR surveys to be able to measure snow depth using ICESat-2. But in these areas where the snow off area LiDAR exists, ICESat-2's global coverage means that these results are scalable. And finally, ICESat-2 has the potential to provide a new global high resolution snow depth data set. There are some next steps that we can continue to look at that can improve the use of ICESat-2 for measuring snow depth. One of those is to determine the appropriate spatial domains for ICESat-2 aggregation. As we saw, a single acquisition date using ICESat-2 can provide very accurate distributed basin median snow depth. But if we want to scale this up, we need to know what spatial domains we can safely aggregate snow depth over. We also propose that assimilating ICESat-2 data with other satellite data, with snow depth pattern information, such as done with Flug et al. 2022, and with snow depth models, could improve global distributed snow depth data sets. We propose that expanding to larger study sites with variable terrain characteristics would help us scale these results. And we think that the snow community should continue to work on techniques that don't rely on snow off aerial LiDAR data sets. One exciting development is that there are some repeat ICESat-2 measurements at mid-latitudes, like in the Western US and in the high mountain Asia region, that are planned for December 2022 through March 2023. And so we'll be eagerly awaiting those repeat measurements to see how well we can measure snow depth using those without aerial LiDAR surveys. To recap the implications of this work, we talked about how ICESat-2 SlideRule can provide high accuracy basin median values in areas with snow off area LiDAR surveys. The global coverage of the satellite means that these results are scalable. And ICESat-2 SlideRule provides a valuable data source that can be used to inform models and be assimilated with other data sources to improve snow depth estimates. I want to say a thank you to everyone who supported me through this process and through my master's work. My grandpa, my family and friends, my communities, both in Yosemite and at Crystal Mountain, my boyfriend, and the grad students in the fishbowl and the treehouse, and in my lab, the Mountain Hydrology Research Group, who helped me. I want to thank my funding sources, the University of Washington, the Burgess Fellowship, and NASA, and I can take questions at this time.
Bart?
Bart.
I have a question. Like in the cascade side, in that out. Like when you showed the 4 years,
Mm-hmm.
there seems to be some very large negative
Mm-hmm.
excursions in the area. Like the big slide one.
I'm glad you asked that question.
And some of the biggest ones occurred right before the first snow observations of the state. I wanted to believe. Is there a pattern or?
Right. So this is getting at potentially some of the differences in reflectance, surface reflectance during the winter versus during the summer. So snow is highly reflective at the green wavelength that ICESat-2 uses. And so it's possible that in the summertime, when the light is reflecting off the ground surface or vegetation, that we're getting fewer returns and that those returns have more variability. Whereas in the winter time, we think that that data is probably more reliable because of the reflectance of snow at that wavelength. There could be other reasons for erroneous summer measurements. We don't know if, say, wildfire smoke in the air can impact those measurements. We definitely know that cloud cover impacts measurements, but perhaps wildfire smoke. There could be other reasons. But in this analysis, we did separate the snow on versus snow off ICESat-2 measurements using data from the snow telemetry stations. And so we were only using snow on data for those calculations.
Like the two biggest downward dips right before
Yeah, in here.
Let's say the next.
Mm-hmm. So, I mean, those timings do likely correspond with wildfires, right, later in the summer. But I don't know for sure. I think that would need to be looked into a little more. Yeah.
Thanks for the nice presentation. I have kind of a similar question on one of the previous slides. It looks like there's an offset on the wooden values during summer also, that they're always below the first slide. So I was wondering, did you perform 3D co-registration between the DEM, the LiDAR DEM, and the ICESat-2 points that you have?
That's another good question. Is it this one?
Yeah.
Okay. So we did a bias correction using the snow off data compared to the snow off ICESat-2 data compared to the snow off aerial LiDAR data. We used the median difference between both snow off data sets to bias correct the entire data set, which did improve accuracy. But again, we talked about how the summer measurements do have a lot of variability. And so there could still be error associated with that. We didn't do a 3D co-registration. I think that would be a great next step. I think it will be difficult because of the sparse measurements from ICESat-2. So that will be a challenge. Enderlin et al. 2022, they just published this fall, and they did do a co-registration, but it resulted in 0 offset in all directions, X, Y, and Z. So they tried that technique with some of the standard products, and it didn't result in any offsets. And they also did this snow on, snow off bias correction. So I think it's worth looking into. I mean, the co-registration between these two different data sets is very important because we're doing direct change detection using 2 data sets. So any offsets between those data sets we don't want to be saying that our snow depth is some offset that doesn't actually reflect true snow. So it's an important component and it's very difficult to do.
The LiDAR is what, 1 meter,
Mm-hmm.
then you have the resolution difference,
Mm-hmm.
and in place of the high curvature, that's systematic error. And that could be then that when you're sampling and taking the difference, you have this kind of value.
Mm-hmm. Yeah, that's true. We did a comparison when we sampled the snow off data. We did it at the original resolution, which was 1 to 3 meters, depending on which data set we were using. And we also did this using lower resolution, like we did this for 20-meter resolution. We coarsened the data set. And the results were not significantly different. But also something to look into. I've also looked at some techniques where you sample the median snow off elevation instead of like for an entire grid cell, looking at aggregated data along a specific region that you think ICESat-2 was sampling. So like an ellipsoid shape that's say 20 meters in length and 10 meters in width, something like that. So that's another technique. And the amount of improvement you see might depend on the study site. Like you said, places that are really rough terrain, it might make more of a difference to use those different sampling techniques. Thank you. Steve.
Thanks again for wonderful presentation. The issue of topography is a fundamental question today. And I last attended a presentation by folks from USGS who are doing the mapping all over again. And I think, if I remember correctly, they anticipate getting their updated maps to within about 9 centimeters of flow truth. And I'm not sure where that is and how many areas in that stage. But the fundamental issue, even when you're running the LiDAR across the thing, is how many ground truth spots you have for putting that down. And I don't know if people are using any of the GPS stations that are physically sitting out there for other purposes, but they're used for a whole range of things now that would be useful. But that's an issue of somebody getting ground right. Then you can check the aircraft against that. And then you can check the satellites against that. So as you say, registering to products is a real challenge. So that's one issue of the basic surveying. There are a hell of a lot better off now. A problem with the USGS mapping, they're trying to map out little channels as well. And they're using the algorithm D8, which is the wrong algorithm to use. And they have others that they could do far better. And after about 12 pixels, D8 is okay, but the fine detail that they're using in that is wrong. They need to be a bit careful about that. The question I never thought about this until the third day. If we have a snow pillow, it's sampling a small patch. But if you really want to say something spatial, if you had to design a nest of snow pillows, even though it's expensive, how many would you need to get a fair sort of a sense of space averaging? And I have no clue on how to do that. Open space is one thing, and create up is totally different. So it's just a difficult observation problem.
Definitely. I mean, this is a pretty known problem in the snow community, is that we have these, sparse point measurements that we're using to interpolate snow depth across an entire watershed. Extrapolate, thank you. And yeah, I think it would depend on the watershed, how many point locations you would need. And also many of these stations are located in like tree clearings because that's where it's easiest to measure, but that doesn't necessarily mean that depth will be representative of locations nearby that have lots of tree cover or that have different like terrain aspect, steepness, things like that. To your point on the aerial LiDAR surveys, this is a point that we go into more detail in for the paper that we submitted. And that is that the aerial LiDAR surveys, I talk about them being the gold standard of snow depth measurements, but the reality is that these surveys are not all created equal, and it really varies on how accurate they are based on the specifics of how they're collected. So if there's ground control points, how many returns per meter squared they get, what elevation the plane is flying at, all sorts of things. And then also the transformations trying to align these data sets into the correct coordinate reference systems, those can introduce errors as well. And there's a lot of details that go into aligning those data sets that can be very confusing and complicated. And I think that's a very important part of this work, is using multiple data sets to do this change detection, trying to get them as well aligned as we can. But there's likely still errors from using different data sets. And that's part of the reason I think we're so excited about these repeat ICESat-2 measurements that are planned for the coming months, because we won't have to do alignment of multiple types of data.
Could you pull up slide number 75, please? Right. You have a ALS telemetry and manual, and that looks like a Campbell Scientific ad for telemetry. Now, I want to point out to everybody, the anemometer in that is a little tough job, and it's useless in very high winds. And the rain gauge is the worst piece of junk you could find anywhere, and there's no way that anything you measure left the rain that you correct it. It's dreadful. So if you want to look at the atmospheric sciences class, go down to the Urban Thought Center, and they have one of those pieces of junk, and they're training the meteorologists to use a piece of rubbish, and they ought to know that. Okay, so just to caution everybody, that's the standard thing with the University of Arizona's program for teaching people hydrology. They have one of those things, and we know they are useless. Okay.
It's a good point. Precipitation is very difficult to measure.
Didn't tell you the brand.
We didn't hear it.
They use the gold with white, okay, and anything with it like it. Oh, good.
You talked about the sparseness of the data. How often are you getting a return trip above a certain point?
So at the poles, they're at exact returns, and that's about every 90 days, 91 days. So if you expand, if you say that we get accurate median snow depth for a basin just from one ICESat-2 date, if you expand your study site, you'll get more ICESat-2 data from multiple different dates. So you have more of a temporal, a longer time series. But we don't yet know exactly how big to make that study area, such that we can still use the median snow depth measured by this one ICESat-2, track to represent snow depth in the entire basin. So we need to look more into that to see how big to make the study sites. But yeah, the return period is about 90 days.
Anything in the chat?
There is nothing in the chat.
During summer, if you get very tall grass field that gets later than over ice, you account for this.
We didn't account for it at all. I think we are relying on the airborne LiDAR, the snow off data, to be accurately measuring the ground surface. But that's one issue, especially at the Methow Valley site, that the snow off data, there were reports of some slight biases due to shrubbery in valley bottoms that would have positively biased the elevation of the ground during that summer flight. And so that is a problem that would also contribute to the lower snow depths that we were measuring due to potentially a positive bias in the summertime in the valley bottoms, where we're able to measure snow depth more accurately. So not all those errors, it's a good point, not all the errors the residuals that we're seeing that I'm reporting, not all of them, I think we can say are due to ICESat-2 errors. I think it's the whole methodology, the combination of data sets, and potential errors from the snow off elevations as well.
You can bring up anything that shows the ICESat measure against the elevation. Any of them will do fine.
Something like the numbers or the,
The time series,
oops.
beauty. So the blue lines up there, in many cases, are these box plots, or they intended to just show the range?
It's the interquartile range.
Different. If you pick up the box plots, or just a few of them, you have a median at 75, 25. You have a bit better sense of how big the spread is. If otherwise, you would just assume the uniform distribution across the basin, and that may not be a bad thing to be assumed based on the median. But if you film as a box plot, you have a much better sense of how tight the stuff is.
You mean like including the whiskers? These are box plots. Okay, yeah. I'm not showing the whisker because it gets really, it feels like a lot of data on the one plot, but that is a good point.
But they're just showing 25 median, 25 median and 75 and 95. There's not a lot to show, and you get a good sense of it.
Mhm. Yeah, thank you.
Hey, Hannah, I got a question online. Can you hear me?
Oh, I think David has a question.
David has a question. Excellent.
Hey, can you hear me?
Yes.
Okay, so great discussion, and great presentation, Hannah. It's nice to see it again. While you got this slide up, I'm wondering about the highest snow depth you measure. It's close to like 3 meters, the median. Yeah, that one. Maybe this is what Steve was asking about. Why is the blue box plot offset from the median? Is that what's going on there?
So he's talking about here.
Yeah.
He's asking why the box plot is offset from the median. I haven't looked into that acquisition date specifically. My assumption was that was just for like the median was also like that it wasn't measuring anything lower than that. But I think we'd have to look into that acquisition date more specifically.
Yeah, let's follow up on that one. Everything else looks fine, but that one looks a little weird. So
Yeah.
we should take a look.
Sounds good. All right, if we have no more questions, we should probably end. Okay. Yes, thank you,
Yes.
Steve. Appreciate it.
Yeah.
Thanks, Bart.